Gathered from old cars, appliances, and assorted steel items, scrap metal represents a reservoir of untapped potential. This mixture of discarded steel is gathered, loaded onto trucks, and transported to a facility equipped with a high-temperature furnace. The first order of business is sorting through the scrap metal, sifting out non-metal materials like plastic or rubber to ensure a clean and efficient process. Once the scrap is cleaned up, it's time for the main event, the high-temperature furnace. This isn't your average oven. We're talking about a massive heat-intensive chamber capable of reaching scorching temperatures. As the scrap steel enters this fiery domain, the furnace cranks up the heat, turning the solid steel into a molten liquid state. This isn't a slow melt. It's a rapid transformation where the heat acts like a powerful alchemist, breaking down the rigid structure of the scrap steel and turning it into a hot flowing river of molten metal. The high temperatures serve a dual purpose, purifying the steel by burning away any impurities and preparing it for the next steps. In practical terms, envision the high-temperature furnace as the engine of this operation, where efficiency and precision matter. The scrap steel, now stripped of contaminants, is loaded into the furnace, and the heat is cranked up to levels that could rival the surface of the sun. This extreme heat acts as a catalyst, rapidly liquefying the steel. The machinery is designed to handle large quantities of scrap at once, maximizing the efficiency of the process. It's not a slow and steady transformation. It's a swift and powerful conversion, turning discarded steel into a molten resource. This molten steel, glowing like liquid fire, is a sight to behold as it flows within the furnace. Think of this process as an industrial ballet, where each step is choreographed for optimal results. The molten steel, now in its liquid form, is ready for its second act. It's like a blank canvas, awaiting the artist's touch. Except in this case, the canvas is a river of hot metal, and the artist is the machinery that shapes and molds it. The molten steel flows through channels and molds, taking on new shapes as it cools and solidifies. The goal is practicality and precision, creating steel bars, plates, or other forms needed for construction and manufacturing. This is not a glamorous metamorphosis. It's a pragmatic process where every ounce of molten metal is carefully harnessed for practical applications. Once it exits the furnace, the molten steel is directed to casting machines or rolling mills. These machines work swiftly, shaping the steel into the desired forms, whether it's long bars for construction projects or broad plates for manufacturing. The liquid steel doesn't get a chance to cool off too much. It's swiftly manipulated into the shapes needed for its next life. Practicality is the name of the game here, with precision cutting machines ensuring that every piece of steel is tailored to meet specific size and shape requirements. Now, let's talk about quality control. In practical terms, this means running tests on the steel to make sure it's up to the task. The molten steel undergoes rigorous testing to ensure it's strong, durable, and free from defects. This isn't about aesthetics. It's about making sure the steel can handle the demands of its intended applications, whether that's supporting structures in construction or becoming a reliable component in manufacturing processes. Let's see the next step of the process of turning steel bars into cast steel pipes. The production of cast steel pipes is a comprehensive process involving several intricate steps that transform raw materials into high-quality, seamless tubular products. It all begins with the manufacture of steel billets, the foundational building blocks of the entire process. These billets, typically cast from molten steel, serve as the starting point for creating robust and versatile steel pipes. The steel billets, often cast in advanced steel plants equipped with cutting-edge technology, have a standard diameter of 230 millimeters. Precision is paramount in this initial phase, as these billets will undergo various treatments to meet stringent industry specifications. Once the steel billets are ready, they are sent to the next stage of production, where a series of forming steps takes place. The first crucial step is the crossroad piercer, followed by the push bench, and finally, the stretch reducing mill. These sequential processes are meticulously designed to shape the billets into seamless tubes with specific dimensions and properties. The continuous casting of round steel billets ensures consistency in the raw material, laying the foundation for a uniform and reliable end product. The actual transformation from solid billets to seamless tubes begins with the D-sharp piercing mill. Rows set at an angle to each other feed the solid round billets over an internal piercer at a speed of 1 meter per second. This ingenious setup turns the billets into tube shells, marking the initiation of the tube forming process. To further refine the shape, mandrel bars are strategically inserted into the pierced shells. The mandrel bar and tube shell then pass through a stand of forming rolls, elongating the pierced shell along the length of the mandrel bar. This elongation process is fundamental in creating a seamless tube, and the pierced shell is extended up to 17 times its original length. At this point, the transformed tube is referred to as a hollow. To facilitate the subsequent stages of production, the hollow, still containing the mandrel bar, undergoes a relay process. Here, the rows expand the hollow, allowing for the removal of the mandrel bar before the tube enters the reheating furnace. The wall thickness of the tube is closely monitored over its entire length using a radiometric gauge. Rigorous quality control measures, such as radiometric inspection, ensure that the seamless hollows meet the specified standards. The seamless hollows then progress to a computer-controlled walking beam furnace, where they are heated to the precise rolling temperature required for the subsequent stretch reducing process. The furnace's design ensures that the hollows rotate uniformly as they traverse the heat source, guaranteeing consistent heating throughout. The 28th stand stretch reducing mill becomes the final shaping stage, imparting the tubes with their definitive geometry, including defined diameters and wall thicknesses. To confirm the accuracy of the production, wall thicknesses are verified over the entire length using a radiometric gauge. The inspection results are graphically displayed, documented, and leveraged to fine-tune and control the rolling process. As the tubes emerge from this intricate production process, they can reach lengths of up to 150 meters. Rapid cooling, achieved through the use of carbide-tipped layer saws, ensures that the tubes attain specific mechanical or performance properties. This cooling phase is a critical step in optimizing the tubes for their intended applications. Once cooled, the tubes can be cut to multiple or final lengths, offering flexibility for various downstream applications. The cast steel pipes produced through this meticulous process serve diverse industries. Some tubes undergo further processing, while others ascend as pre-material for drawing or are directed to drill pipe manufacturing plants. The applications are vast, ranging from commercial vehicles and the automotive industry to the production of mechanical tubes, boiler pressure tubes, high-temperature resistant tubes, and pipes for the oil and gas industry. Each type of tube is crafted to meet specific industry requirements, demonstrating the adaptability and versatility of the production process. For specialized applications, such as drill pipes, tubes can be shipped with ends upset according to API specifications. The manufacturing facility offers special upsets for drill pipes, including integral and premium connections. The process of heating pipe ends to forging temperatures with induction heaters and subsequently upsetting them to the required contour in up to 3 forming steps ensures that the tubes meet the stringent standards demanded by the industry. Following the initial production stages, the tubes undergo a crucial heat treatment process. In the austenitizing furnace, the pipe is heated to a temperature that induces a change in its microstructure, setting the stage for subsequent hardening through rapid cooling in the quenching process. The hardened pipes are then tempered in a temper furnace to achieve the desired strength level. Rapid cooling of an austenite steel creates a defined microstructure, characterized by exceptional hardness and strength. This hardening step is a prerequisite for tempering the tubes to the required strength level. In the tempering furnace, the hardened tubes are heated to a specific temperature and held at this temperature for a defined length of time, culminating in the attainment of the required steel grade. The heat-treated tubes then undergo straightening in rotary straightening machines, ensuring that each tube meets the specified quality standards. Non-destructive testing is a crucial aspect of the quality control process, involving electromagnetic inspection and the inspection of pipe ends using ultraviolet magnetic particles. During electromagnetic inspection, the wall thickness is measured using phased array ultrasonic methods, providing a comprehensive assessment of the tube's integrity. In conclusion, the production process from steel billets to cast steel pipes is a sophisticated and highly controlled series of steps, each contributing to the creation of seamless, high-quality tubes. This process, rooted in precision engineering and cutting-edge technology, exemplifies the dedication to quality and performance that characterizes the steel tube manufacturing industry. From the initial casting of steel billets to the final inspection and testing of heat-treated tubes, every stage reflects a commitment to excellence, ensuring that the resulting cast steel pipes meet the diverse needs of industries worldwide.